Okay, so good morning and happy New Year to everybody. So we resume our Crypto Cafe talks for 2025, and we have our own Edoardo Persichetti who will talk about digital signatures from cryptographic group actions. Thank you very much.
Thank you, Francesco, Shi, and Veronica. I mean, I am happy to give another talk. I think this is actually the talk I wanted to give last time, and then it finally came the time. It's a recent work joint with Giacomo Borin, Federico Pintore, Paolo Santini, and Klein Reinders. So, okay, let me see. Yeah. So this is kind of the outline of the talk. I will give a motivation for the work and some background, and talk about digital signatures, and then kind of give an overview of our techniques, the techniques that we analyzed, and give some conclusions. So the motivation is kind of always the same for our work. I think we work in post-quantum crypto because we are getting ready for quantum computers to arrive and smash everything. So the post-quantum standardization call now has been evolving for several years, and we have a lot of areas of research. And in particular, I personally work in code-based cryptography, but as you know, we cover everything at FAU. And a particular trend that emerged in the last few years more prominently regards cryptographic group actions. And these are objects that come from algebra in a very intuitive way. So a group action is simply a map, right, acting on a set coming from a group in the following way. And we require it to be compatible with the group operation. And in particular, in cryptography, we're interested in cryptographic group actions. So actions that have additional properties, such as efficient evaluation, sampling, and membership testing, and especially hard problems behind them, such as the group action vectorization problem, also sometimes known as the group action inverse problem, which is exactly the problem that asks, given two set elements, mapped by a certain group element, to recover the group element that maps them. Right, so this kind of gives a very intuitive application in cryptography. For example, if we take a group of order prime order, and then we take the group ZP star of exponents, let's say, then this is exactly the vectorization problem, is exactly DLP in this set. Right, and even with just this one simple idea of group action, we created a huge literature of cryptography, very preciously, in fact. And the thing with this cryptography is that, of course, it's very special, right? So we are having a group acting on a set, which is another group, and this leads to a lot of useful properties. For example, we have commutativity, we have possibility of group law, we have a lot of design options, but this is also its downfall in a sense, because this makes the action not post-quantum, right? And in recent times, isogenies kind of showed the world that we can use group actions in a post-quantum way, right? And then, we started investigating other post-quantum group actions, such as code equivalence, for example, or lattice isomorphism. They were always kind of behind, lingering, but they've never been investigated on their own, if you want, in a cryptographic, under a cryptographic lens, right? So in this work, we kind of considered the idea of constructing these digital signature schemes from group actions, which has been one of the main trends in the last few years. So a quick step back to present the idea of digital signatures. Of course, we have two main avenues to construct digital signatures. One is to use a hash and sign framework, where we use trapdoors, such as in RSA. And then, we simply kind of perform what students learned in their introductory course to crypto as like a reverse encryption, right? So we receive a message that we need to sign, we apply the trapdoor one-way function to it. Well, first we hash it, then we apply the trapdoor one-way function to it, and then we generate a signature in this way, and then verification is trivial. It just requires computing the function on it. So This intuitively leads to very complex signatures, but the signing process is the complicated one, right? Because it requires inverting this function with the trapdoor, and this has to be leakage-free. It turns out this is kind of very complex to design, right? Again, you can believe that. And in fact, in PQC, this is often a serious issue. So the best example that we have is kind of Falcon, which was selected for standardization, and is the only one chosen by NIST, at least so far, but practitioners are kind of reluctant to deploy it so far, and standardization is kind of proceeding a little slower, and certainly NIST is recommending other types of schemes for general use. And what are these other types of schemes? So these are usually built on the basis of zero-knowledge protocols. So we use a protocol that is an interactive protocol between a prover and a verifier to prove the knowledge of a certain witness to a statement, right? So imagine a relation, and then you have a witness that shows that this relation is true. And we want to do it in zero knowledge, so without actually revealing anything about the secret. So we have a 3-step or sometimes 5-step or 7-step, so several versions, but in the simpler case, we have this kind of 3-step protocol, which is known as a sigma protocol, in which the prover commits to some data, and the verifier receives a challenge, and then the prover computes a response, which the verifier is able to check for correctness. And of course, we want the honest verifier to always get accepted. We want zero knowledge, like we mentioned, so that no information is leaked about the secret. And we would like to have some bounds, right? So the concept of soundness determines how sound the protocol is. So what is the chance that an impersonator can actually cheat and pass verification without knowing the secret? And once we have a zero-knowledge protocol, we can easily turn it into a signature scheme. We will talk about this. But again, we can see an example. Taking the group action that we had before, right? We can the discrete logarithm one. We can build a simple sigma protocol, right? We have our statement, which is a pair of group elements, and this is kind of deceiving because, of course, we are talking here about group elements, but this is the set that the exponent is acting on, right? So we have H and G. We know they are mapped by an exponent S. And to prove the knowledge of S, we commit to another random instance, sage to the R. Then we receive a challenge from a certain challenge set, and we reply with R minus CS. And you can see that the verifier is able to check whether the commitment and the response are actually matching. Yes, and of course the soundness here depends on the challenge set. So in the simpler case, we can even just take the challenge to be a single bit, and this leads to a standardized error of 1/2. Right, so in one case, that means that we're applying with just R, and we're kind of checking consistency of the protocol. And in the other case, we're applying with R minus S, and we're checking that actually the private key matches correctly with the commitment. And well, you can see that, in fact, a malicious prover can always cheat in 1/2 of the cases. So building on the base of this, we can adapt this to like generic group actions, right? And so to do this, we take a sigma protocol, we apply the Fisher-Schmidt transformation. So we remove the interaction by replacing the challenge generation with a randomly generated value. And then we repeat a number of times that it's necessary to bring down the soundness error. So if we do a certain number of repetitions of the protocol, and in each round we have a certain chance of cheating, then passing every single round, it's a simple amplification of the soundness, right? So usually this leads to very efficient schemes, as short signatures clearly showed. And we have very strong security guarantees. These are guaranteed by rigorous soundness and zero knowledge proofs. We don't even need a trapdoor, right? So there's several advantages to this approach. But however, the approach requires a lot of improvements from this kind of basic version to arrive to a shape that is actually useful in cryptography, at least among the post-quantum schemes, right? So we have a big array of techniques that are employed to improve such a protocol, some generic and some that actually are exclusive to group action or even to certain group actions. And our goal from the outset was to study them and classify them and understand which ones are interesting when and how they interact with each other and so on. So this was kind of our idea, to create a taxonomy of such techniques so that they can serve as a guide for the designer. And so with this in mind, we can, if there are no questions up to this point, I would assume this is kind of more or less general knowledge, but I can move on to the description of the individual techniques. Okay, so maybe we start from the crux, I would say, of the matter, which is Fiat-Shamir, right? So Fiat-Shamir is a transformation that dates back to the 1980s. And it's a very clever idea, as I was describing before in a summary, to turn a Sigma protocol into a digital signature scheme. So to be more precise, what we do, we take a Sigma protocol and a hash function that maps into the challenge set. And then our key generation algorithm simply takes the statement from the relation that we know the knowledge of, we're able to prove the knowledge of using our Sigma protocol, right? We set the verification key equal to the statement and the signing key equal to the witness. We then sign by executing the steps of the Sigma protocol. P1 is the commit step. We then hash this commitment together with the message to get the challenge, and then P2 is the second step of the prover, which is the response step. Then we output the signature, which is the concatenation of the commitment and the response, Sigma 1 and Sigma 3. And to verify, the verifier simply takes the signature together with message and verification key, recomputes the commitment, and then runs the verification algorithm as in the Sigma protocol. So Fiat and Shamir were able to prove that by doing this, you obtain a signature scheme that is existentially enforceable in the CMA model. And this is true up to, of course, the soundness error of the protocol pi underneath. So, of course, if we are going to sign, we need to bring this down to the security level that is the desired security level of the signature scheme. So we need to have a soundness error of, say, 2 to the minus 128, for example. If, furthermore, the commitment can be publicly recomputed from the challenge of the response, and of course the public statement, then we actually say that the scheme is commitment recoverable. And this allows to simplify the scheme, because instead of having to transmit the commitment, we can transmit the challenge. And instead of recomputing the challenge, we actually take the challenge, recompute the commitment instead, and then check that the challenge was correctly generated. And this often is advantageous because the size of Sigma 2, the size of the challenge, is much, much smaller than the size of the commitment. So this is straightforward improvement, which is kind of built in a lot of Sigma protocols, but it doesn't have to be, right? So I have come across some protocols that could use a commitment that was, however, impossible to recover because, for example, it was not a one-to-one map, et cetera, and so, oops, I think we have a user that cannot see any slides.
Oh no, is it the case for everybody? Veronica, can you see the slides?
Can everyone see the slides?
We do see the slides, at least on our side. I don't know, Veronica, if she can see the slides.
Or someone else on?
Yes, so I yes, so I think just
Okay.
it's a problem with one person.
Okay. Sorry for that. So maybe I should move on to, hopefully it can get fixed. Okay, so it looks like it's should be fixed out. Right, so Fiat-Shamir, so yeah, so Fiat-Shamir is the first kind of intuitive transformation. This is not news. And then we have parallel repetitions, which is the other transformation that I mentioned. I don't want to spend too much time on this, but you can see that formally we can define it as a transformation transforming a Sigma protocol pi into a new Sigma protocol pi first, or pi prime. This is kind of also the formalism that we use in our work. So we have a commitment set, which is simply a Cartesian product, t times, right? And same for the challenge and response set. And what we do is that we simply repeat the protocol t times in parallel, and each transcript is just a copy of a typical Sigma protocol transcript. right? And then the verification just executes T times the verification algorithm and outputs 1 if it's passed every time. So this intuitively raises the soundness error, reduces the soundness error from, say, epsilon to epsilon to the power of T. And so one typical avenue to obtain signature schemes is then do parallel repetitions. For example, having a soundness of 1/2 means that you have to repeat exactly lambda times, where lambda is your security parameter, and then you obtain the desired security level. Can we do better than this? And this is the question, and the answer thankfully is positive. So let's take now that generic protocol for group actions that I mentioned before, right? This is kind of follows the blueprint that we saw in the generic DLP-based protocol, where we replace our powers in a group by generic set elements and group element matching them, right? So we have now that the statement is a pair of elements y and x, and they are obtained via G applied to X as a group action. And the rest is really just a translation, right? So what we do is we, again, generate a commitment by taking a random instance, and we receive a challenge from a certain challenge set, and we respond with G bar times G to the negative C. So we have this inverse element, which is the one that allows us to map the public key with the commitment, okay? So after a while, starting to describe the schemes became more and more complicated. And this is why we thought it was useful to visualize them, which instead, I think, renders the entire method a lot more easy to follow. So in this case, you can already see that if we draw this sort of triangle, we have a very easy example of what we call action graph, right? Because it's a graph that illustrates the action of this group action. And so if X and Y constitute the public key, essentially what we are showing is that an honest prover can always complete this diagram, right? Where X tilde is my commitment, and I can by X by actually transmitting the random element used to generate the commitment. So this corresponds to the case C equals 0. And otherwise, we can compute it from the Y, from the right, which is the other part, if you want, to the public key. And what we're proving is exactly that in this way, we know the map between X and Y. So it's possible to build what's called an extractor that shows that if you can actually answer always from both sides, then you can immediately recover what is the map between X and Y. This should be intuitive. You just take one element times the inverse of the other, and that will yield exactly the secret one. Okay, so in the simple situation, what we have is we have a consistency check from the left, and then an actual challenge from the right, and these two combined yield the protocol. Okay, it's important to notice that in the case equals 0, in fact, we are answering with a purely random element, so this consistency check is actually very light. Because we don't need to transmit this element, we can just replace it with a seed that then gets fed to a pseudo-random number generator, right? So this is kind of, again, very intuitive optimization that comes into play. All right, so then what's the idea? We start from this, we iterate T times or lambda times, and then we apply Fiat-Shamir and we're done. Well, then, of course, this is not very optimized. Everything okay? Yeah, so this is not an extremely optimized protocol, of course, and this is where the true, if you want, optimizations come into play. So things like substituting random elements for seeds are extremely intuitive. Let's see something that is a little bit less trivial. When I apply Fiat-Shamir parallel repetition, I obtain a signature size, which is essentially half of the times the size of a seed, and half of the times the length of a group element that I'm transmitting in the case C equal 1, right? Plus some randomness that I used to generate, first of all, the salt and the size of the challenge, right? In the worst case, if I'm unlucky and I draw T times the challenge equal to 1, then I get T times LG, right? So we want to focus on this size here to see how we can improve that. The first approach is reducing the signature size by reducing the amount of times that the protocol needs to be iterated, right? So clearly we've seen here that we have this t, which is the number of iterations, and this is depending on the fact that my sandwich is 1/2. So I have to repeat the protocol many times. So if I could reduce the amount of times that the protocol needs to be iterated, then I would immediately and intuitively reduce the signature size. So we can do this by reducing soundness. And we do this reduction in soundness by increasing the number of public keys. So for short, what we do, instead of taking a statement of the form xy and completing the previous action graph that kind of looks like a triangle, we take a statement of the form x, y1, ys, where all these elements y1, ys are related to x via their own witness, gi, say. And then we show that we are able to complete this action graph, right? So what we can prove is that we know these elements here, and each of them form their own triangle with x. Okay, so with this multiple keys optimization, the prover commitment phase is exactly the same as before. But when we sample a challenge now, the challenge 0 is the same as before here, matching x to x tilde, but the challenge different from 0 now is not going to be just binary, it's going to be either 1, 2, 3, or all the way up to s. And that means that we respond with the element, this is a typo here, should be ch at the index, with the element that matches exactly the key corresponding to the chosen challenge. So if my challenge is 3, then I will reply from the 3rd public key. If my challenge is 5, I will reply from the 5th public key, and so on. Okay, and then the verifier algorithm is exactly the same, but the verifier will select exactly that part of the public key that is corresponding to the challenge to verify the statement. Okay, so all we're doing is we are exploding the number of public keys, and this means that now my challenge set is of size s+1, right? We have the 0 challenge and then s different y's, and the challenge can ask to complete the diagram from any of them. Okay, so what this does is that we reduce the soundness error to 1 over s+1. And in principle, we could just take this s+1 to be so big that we just do the protocol one time and we're done. But of course, for practical realizations of a signature scheme, this is not enough, right? And so maybe a combination of this with repetitions, actually without the maybe, a combination of this with repetition is the way to go. So we just take a number of repetitions that is lambda divided by log of s+1, where s is kind of arbitrarily chosen, right? So we treat s as a parameter, and then the number of repetitions kind of follows immediately. And this shrinks the average signature size, as you can imagine. We now have 1 over s+1 seeds that we can expect on average, and then s over s+1 group elements. And what is important about this is that it's a trade-off with the public key size, right? So the public key size goes linearly in S, and so it gets very big very quickly. So we choose a value of S which depends on the specific instantiation of the group action. For example, if we're doing this with isogenies, where the objects are very small, we can afford a reasonably large amount of public keys. Whereas if we're doing this with code equivalence and the set elements are matrices, then we reasonably can only expect to do this for, say, S within 3, 4, 5, 10. Okay. The second optimization that is kind of standard right now in literature is doing almost the opposite thing. Well, I'm saying almost, but by this what I mean is that instead of reducing the number of iterations, we're actually going to just alter the length of these iterations. And in the end, this will result, as we will see, in actually more iterations, which seem kind of contradictory, but hopefully will make sense. Okay, so the key of this optimization, which we call fixed rate challenges, is that, in fact, as we have noticed in all these previous formats, for example, this one, right, the cases where our challenge is 0 are actually very light because we don't have to transmit group elements. So here, transmit only a seed of size lambda. And so we want to kind of maximize these cases artificially and minimize the cases where we actually have to send a group action. To do this, we follow then a different pattern. So rather than sampling every round of the repetitions uniformly at random, we choose a distribution with a fixed weight. So we just alter. As you can see, this looks a lot like the formalization of the parallel repetition optimization, where we have t repetitions, but now our t repetitions in the challenge set are not independent from each other. They're not chosen uniformly at random. They are chosen from some sort of binomial distribution so that the weight of this challenge string is a fixed value w, which is again now a parameter of the scheme, right? And then the rest proceeds exactly as before. So we just verify every single round and accept if all rounds are passed. So what this does to our scheme, right, is that if you see here the action graph, we now have a triangle, right? And then we have several iterations of the scheme. And then sometimes we apply from the left, sometimes we apply to the right. In this case, of course, for obvious reasons, I could only represent 5 iterations, which is not enough to show the disparity. But we want the number of verifications from the right to be much, much smaller than the number of iterations on the left. So in practice, we can compute the standard error, which is now 1 over this binomial coefficient, and then choose t and w so that we obtain a good trade-off. Right now, in fact, the size of the signature is exact. There is no more randomness because we know exactly how many zeros and how many ones we are expecting. And so we have t minus w seeds and then w group elements. Right? So this soundness error can be selected so that w is much, much smaller than t. And this usually brings a big advantage to the signature size, exactly because this asymmetry between the size of a seed and the size of a group element, okay? Typically, though, what this does is that the number of repetition needs to increase because we are choosing from a different distribution, okay? So this, in fact, is a trade-off, but not with public key size, but rather with computational resources, because now we are doing a longer amount of rounds, and the signature will get smaller because many of the rounds only transmit a seed. But in fact, we are still computing several group action evaluations, for example. Right? So signing a verification could get, in principle, slower. And now, because we have many seeds to transmit, and this is independent of this optimization, but it becomes even more important with this optimization, right? So we could do this always, but especially because we have several seeds that we need to send, it makes sense to transmit these seeds efficiently. And we know in several applications of mathematics that trees usually allow to do things very efficiently, right? Not just transmitting seeds, but like searching and sorting, etc. And so this is the case in cryptography as well, right? So this family of trees that are called seed trees sometimes, or GGM trees after Goldwasser, Micali, Goldreich, I believe, are an efficient way of transmitting pseudorandom objects. Right? So they are, in fact, if you want, a specific instantiation of a larger class of primitives that we call puncturable pseudorandom functions. So the idea here is to generate T seeds in a recursive way, right? So we take a binary tree, we generate a binary tree where we start from a root, and then we use each node to generate 2 children. And so in this way, we get a perfect binary tree, right? With at every level, we get a number of leaves, or a number of nodes, I should say, that is a power of 2, up until we reach the desired number of leaves. Yes. Now, in practice, this number will not always be a power of 2 in our scheme parameter. So when t is not a power of 2, what we can do is adapt the techniques, right, to asymmetrically generate this tree. And here we have 2 examples with t equals 6. So, for example, if we were doing 6 repetition of the scheme, pardon me, or with t equal 14, right? And now at the bottom level, we have these leaves, and these leaves can be our T seeds, right, that we use in each round for our algorithm. Now, of course, not in every round we will use seeds, right? But in some rounds, we actually send, like we know, group elements for the challenges that are not 0, right? So we have to kind of puncture this tree. That's why it's called a puncturable random function. And so Some of these leaves will be transmitted, but not all of them. And what is important is that because each node at each level is children, right? So it's generated via application of pseudorandom function. If I have, for example, to transmit leaves 1 to 4, it's enough for me to just transmit the seed here at the first level and then regenerate the seeds myself. So I don't have to transmit 4. Okay, so there is a precise strategy for generating the tree, and then for creating the best path, right, that minimizes the amount of seeds to be transmitted. Here we have 2 examples with 8 leaves, right? So imagine we're doing 8 repetitions. We have 8 seeds. In principle, we do not need all of them, but we need most of them because that's the idea, right, with the fixed weight optimization. And so even in the simplest case, when we have just 1 seed that does not need to be transmitted, and everyone else needs to be transmitted. So here the gray one is what we don't want to transmit. That's the round where we sent a group element. Then the remaining 7 seeds can be communicated with just 3. One is the leaf next to it, and then there's like this one and the other one that are the parents. And similarly, in fact, if the distribution is kind of a lucky one, we can transmit 5 seeds with just 3 seeds here. So this depends, of course, on, as you can imagine, where the seeds are located that we need to transmit and how many of them. Right. So other than that, what this transformation does, C3, is just modify the way in which seeds are transmitted. So we start from a seed root, right? We produce T leaves up to exactly the number of rounds that we need to iterate our protocol. We use this to generate the commitment, and then we release the ones that are necessary for the rounds corresponding to the challenge equal to 0. Okay, and then the verifier is able to recover the necessary ones from the internal ones and verify the validity. So instead of transmitting these seeds kind of in the obvious way, we transmit them using a tree structure. And so, of course, what I was saying, the important thing is understanding what is the number of nodes that needs to be transmitted. In particular, we want a bound that gives us the maximum number of nodes that we can expect. And we devised a new bound. There is an intuitive one that kind of is logarithmic in nature for the case where t is a power of 2. But like I said, in our case, often t is not a power of 2, but maybe it's a sum of powers of 2, and then we can easily characterize the bound in this way. So this is kind of a new contribution, but it turned out to be extremely useful to gauge the impact of this seed tree. In fact, if we release all seeds but one, it's a very special case. It's occasionally helpful. Then this is clearly just log D. Right, and it's important to notice that doing this incurs no security loss. So we obtain seeds that are just as good as the one that we were generating in kind of the brute force way. All right, so what do we have? We have a basic kind of sigma protocol based on group actions, and then we have 2 different ways of reducing signature size. One by increasing the public key size and reducing the number of iterations, and then one that instead kind of tinkers with the number of iterations by fixing many of them to be 1, or if you want, many of them to be 0. And seeds can always be transmitted efficiently. This is kind of where we are and where we were before the beginning of our work, if you want. And this is a lot of these optimizations were very well known in literature, but they were never kind of affronted all together and compiled together. And in fact, one thing that you would immediately notice is that, okay, how do these 2 things interact with each other? Like, can we combine them? And the answer is yes, and we will see them later. And then we have a newer approach to efficiency, which emerged very recently and usually goes under the name of MPC in the head. And from our point of view, we were very happy that we were able to actually fit it in our framework in formalization. Because in fact, we can look at it as doing a different type of interaction with the action graph. So The formal description of the optimization is a little bit more complex, but essentially what you can see is that instead of having the X and Y pair defines the statement, what we do is that we go from X to XM if you want, and then we map each one of them as a chain via respective elements, right? And then what we do is that we commit to all of them, and when we get a challenge, the challenge will be sampled from the set 0M, and unless we are asked to provide the last one, what we can do, sorry, this is the last one, the challenge equal to M, is that we can provide the elements up to the point where the chain is being queried, and then start from the right on the other side. So this is best visualized in this way. You can see that we have X and Y, and instead of a single element used for commitment, we have M of them, so we kind of walk a path in this action graph, and then we can be queried on any one of them, so we can be asked to interrupt the path at any point, right? So again, this is a special case where we asked just the last one, and in this case, you can see that we just reply with all of the elements mapping the path. This is kind of the special case. Kind of looks like the special case we replied from the left before. And if instead we have a non-trivial challenge, then what we do is we walk the path from the left up until the interaction, and then we walk the path, we resume the path from the right and complete the chain. And so this proves the knowledge of this link that is being queried. Okay. So essentially, and this is why the technique, is called MPC in the head. This is a simulation of n+1 users doing a multi-party computation evaluation of the group action. So they are computing this group action all together by sequentially applying random group elements. And so the response then simulates revealing all the steps except the challenge +1. Okay. So it's intuitive to see that then this reduces the standard error to 1 over n+1 because we have n+1 possible interruptions on this path. And we can easily combine this with parallel repetition and Fiat-Shamir, and then this becomes a signature scheme with this average signature size. And if we will see that the average signature size depends on number of repetitions, T, and number of elements that we put in our work, M. And like I said, the case where we interrupt at the end, the challenge equal to the last one, is the special one we can just send seeds. We send M times M seeds. And then the other ones are kind of normal cases where we had to send the group element, all right? So it's kind of emerged independently in literature, and then I guess people were trying, us included, to build schemes using MPC in the head with group actions, and we were wondering if that was better or worse, or how did it compare, and if it was comparable with the previous techniques. And this is kind of a big chunk of the motivation for this work. As a result of that, we looked deeper into MPC in the head. And once we had the realization that this is just a longer path, a longer walk in the action graph, then we wondered if it was actually really necessary to provide every single link in the path, even up to the interruption, right? And the answer is that, in fact, no, this is not necessary. So what we can do is that we can combine several individual paths into a single path up until the point where we need to interrupt if we commit to them. So we now use some intermediate commitments, right? So we compute a first commitment and then we hash it. And then we keep doing this like iteratively to generate all the next commitments so that the final commitment value is the result of the commitment, intermediate commitment steps. And then the transformation is exactly the same as before, but what we can do is just combine steps before. So rather than looking at the description again, I think it's helpful to see the action graph, which is at the basis of the entire work. And you will see here that we have various instances, right? So here, for example, if we interrupt a challenge equal to 2, instead of revealing the path going from X to X1 and then from X1 to X2, we combine these two together into a single path, right? And then we commit a proof for that. And then we have other various possible types of challenges. For example, we have challenge equal to 4, and we combine the first 4 elements that with, if you want to plane a piece in the head, would reveal individually, and we just combine them all into a single part, and then we add a proof that these were computed properly. Okay, and this can be done if you want from the left or from the right. So we have left skips and right skips, which lead to kind of 2 different versions of this skipping edges optimization. So this yields the same soundness error and public key size as before, but now we reduce the number of group action evaluations that are necessary. Okay, and so this kind of, in fact, because it's upper bounded by 1 plus m over 2, it decreases by a factor that is almost equal to 2. So we basically halve the number of group action evaluations. So what this really achieves is a computational speed up in the protocol, right? In fact, on average, the signature size is a little bit different, but the maximum signature size ends up being exactly the same. So this is an overview, right, of where we were with optimizations. We have kind of traditional optimizations, such as improving or tinkering with number of repetitions or public keys, and then we had this kind of new trend emerging with MPC in the head. And we decided to study a little deeper how it applied to group actions, and this was the result of it. And in fact, there is one more optimization that we considered, but this is a little bit peculiar because it decreases the cost, but only in the case when the group action is commutative. The idea is that if the group action is commutative, we can walk these paths in several ways. So we can rearrange paths and generate new instances for our challenges. And so if we take the protocol pi that is obtained via the MPC transformation, what we do is that we can just rearrange, like in a hypercube, looking from one side, from another side, and then obtain several challenges in this way. So here you can see it visually. Again, this is kind of the underlying motivation for our action graph formalization, that if I have an action graph for 4 parties, right, I can generate commitments first, and then we have challenges of the type 0, 0, 1, 0, 1, 1, and we immediately get more challenges, but we can kind of reuse the same setup. Right, so this kind of yields the same soundness error and public key size, but now we don't have to compute all these individual challenges because we are reusing the same setup multiple times. We have far fewer group action evaluations for commitment and verification. So then we drop signing and verification time consistently. And of course, this means that we need to perform operations in the group, which is convenient when the group operations are very fast. But also what needs to be kept in mind, and I'll go back here, is that this only works when the group action is commutative, because we need to be able to go back and forth in this action graph. So this applies, for example, to the case of commutative group actions, such as the ones that typically come with isogenies, but not, for example, for group actions such as code equivalence or lattice isomorphisms that are not commutative. And once we have identified all the transformations that we wanted to work with, then the task became to illustrate how they combine with each other. So again, like before, I'm interested in giving an overview of what this is, rather than going deeper into every one of them. For the sake of fairness, I should say that the paper is quite long and technical because we formalized each of these optimizations separately and in detail. So it's impossible to fit it all into one talk, but I hope that at least the flavor will be clear. So some optimizations are intuitive, some combinations of them are equally intuitive, and then some are less so. So the first thing to do is, I mean, at least from an organizational point of view, is to analyze how we can combine fixed weight challenges with other things, right? So two optimizations are intuitively perfect for each other, and this is using seed trees with the fixed weight challenges, because we have now many seeds and we can transmit them efficiently. So now we have an exact signature size like before, but rather than having T minus W seeds, we have actually a number of seeds which corresponds to the upper bound connected to the tree optimization. In addition, we can always combine this with multiple keys. And now our sumness error, rather than being T choose W inverse, is also multiplied by this factor 1 over S to the W, because we now have S public keys. So in fact, you can imagine that you have key rounds, and the challenges are either 0, where you send a seed, and these are many challenges, but if they are not 0, they're not simply 1, they could be 1, 2, 3, up to S, which correspond to the specific public key selected for verification. Okay, so now we talk about a proper Hamming weight string, but it's not a binary string, it's a string with values between 0 and S. Okay, so we have in fact the same signature formula as above, but now the number of rounds that is necessary will change. We are trading number of rounds with public key size. Right? So this combination is the one that comes first because it's the one that is most commonly used in literature, is what it was used in LES, MEDS, and ALTEC, which are 3 schemes that use group actions in literature that were submitted to NIST standardization. Now LES is in round 2, and MEDS and ALTEC were put aside because from a certain point of view, if you want, they're kind of similar, right? So LES is based on Hamming and metric code equivalence, MEDS uses matrix codes, and ALTEC uses this kind of alternating tensors. And in all of these, like intuitively, this is the combination that was used. So part of the outcome of this work is to verify whether this is the most efficient combination possible or not. So what happens if we try to do MPC in the head combinations? Then we use a C3 to transmit the M leaves, right, corresponding to the MPC simulation. And the signature size changes as follows. And in addition, we can compute this optimization with multiple keys. We can combine them together like we did for the fixed weight. And we now have a challenge space per round that corresponds to this Cartesian product, right? So it's like essentially 0 M-1 times 1S united with the trivial challenge where we send seeds. The M challenge is now what was the 0 challenge in the fixed weight optimization, is the one where we send purely random objects. So in the end, we have a sumness error of 1 over Sm plus 1, which greatly diminishes the number of repetitions needed for the scheme. And again, we can trade the number of repetitions with the public key size. Instead, we can combine this with fixed weight challenges. So we now have fixed weight challenges in the MPC graph, and we try to exploit the difference between the non-M challenge, which are the non-random ones, and the M challenge, which is the random one, so that the latter occurs only every time. So this is essentially an adaptation of fixed weight to the case of M versus non-M challenges. So it's not properly Hamming weight anymore, right? But in the same way, it kind of works, and it reduces the sumness error as follows, which is what we had before, or similar to what we had before. And so then now we have an exact signature size given by this formula. So what you will notice is that we have, again, a C3 playing a big role here, and then W elements that require kind of group element transmission, okay? And then finally, we can combine all of these together, including the public key, the multiple public key optimization. And again, we have much smaller sumness error, and we are taking this with public key size. Putting this all together yields several possible combinations, but in fact, to analyze them all singularly would be nearly impossible, certainly impossible in the scope of a talk. But we reunited them all in a table, and what was interesting is that this table then becomes exactly the taxonomy and the guide that we had in mind. So we can see how different combinations of these techniques together interact and what kind of the sizes that they are yielding. And for example, you can see that some of them obtain different sizes, but also then increase the public key size by a certain factor. And we then counted signing verification time in terms of group action evaluations that are necessary. And of course, all the necessary conditions. So in the end, this is a very detailed guide of what happens with group actions when we apply all these different optimizations together. Of course, we have a dedicated section in our work analyze the skipping edges, both because it's a new optimization and because it's a little bit more complex to discuss. So it will not fit into this talk, but we did analyze that as well, as you can see from the table. So what can we conclude? So in the end, after having presented the optimization, after having discussed how they combine with each other, we can draw some conclusions. We can present an analysis. First, in practice, we are able to show the fixed weight challenges by itself. And I shouldn't say by itself, I would say without other things. So we just combine it with C3. We have seen the public keys, multiple public keys can be always applied, whatever optimization we choose to include. So essentially, fixed weight with C3 is almost always better than MPC in the head. So we present a three-step argument that shows that essentially we have a difference between two protocols. One, P1, which we obtain using a combination of MPC in the head and multiple keys, and one, which is P2, which just uses fixed weight and multiple keys. And we just adjust the number of rounds so that they are comparable. And in fact, the two protocols have the same computational complexity, but one just has more steps to do. So protocol Pi2 has a larger challenge space, which is the one, again, that uses fixed weight challenges instead of MPC in the head. And therefore, we need to do fewer repetitions as soon as m is greater or equal to and t is greater or equal to 7. So this is why we say it's almost always better for schemes based on group action to just do what people have always done, to use fixed weight challenges and multiple keys with the C3. However, when we factor in skipping edges, we were able to do some experiments and see that if we now combine skipping edges with fixed weight challenges, we can outperform the protocol using only fixed weight challenges. And we can just compare the number of group action evaluations that are necessary in the verification. And as you can see, like from the graph, the verification cost is smaller, at least in some cases. So this leads to a potential improvement in this case. So what we did in our work, we carefully analyzed all the existing schemes in light of our results, and we concluded that for less meds and Altec, that currently use a combination of fixed weight challenges, multiple keys, and C3, we would not benefit from switching from the current setup to MPC in the head combinations. However, because of what we said before, we looked also at the case of isogeny-based schemes, such as C-Fish and Scallop, and we have potential for improvement because these group actions are commutative and we are able to factor in even the hypercube in there. However, because these sizes are already quite small for isogenies, yes, there is an improvement from a technical point of view, but it's quite minor in terms of the resulting size, something ranging between 32 to 64 bytes. So it's not something that should justify, in my mind, switching to a new paradigm. So this was kind of an interesting analysis in the end, because we did not know that and we did not expect, but we concluded somehow, interestingly, that what is currently being done for group action schemes is near optimal. And with this, I would like to conclude my talk, and I have, of course, some references for who is interested. Thank you.
Any questions? Thank you, Edoardo, for this very comprehensive talk. Okay, any questions from the audience? Yes, Daniel.
I'm interested in the isogeny actions, and I'm wondering in digital signatures how I guess important they are compared to the other actions.
I would say that isogeny-based actions are quite important. They offer very interesting schemes with very unique performance profile, and they're different in a sense. So they have several properties. The most obvious one being commutativity, but not the only one. They are different from other group actions that we consider in post-quantum crypto. So it's always useful to consider them in the picture.
Okay, any other question? No, okay. Then let's thank Edoardo again. Thank you.
Thank you for joining me. And if you want any references or pointers, you're welcome to contact me.
Okay.